Hello, and welcome to my final presentation video for ENME 489Y Remote Sensing at the University of Maryland. My target is the academic testudo. The academic testudo is located right by the Center for Young Children, and it looks like this. As you can see here, there's a number of distinct features that we're trying to capture. So we have this black-chested testudo, which is going to be a little hard to pick up as it turns out. Then we have this very small hole, about 2 centimeters in diameter, and then we have this book. Panning up, we can see that the testudo has this little mask, reminiscent of maybe a Teenage Mutant Ninja Turtle. Worried about the contrast between the black and then the green, as the black is going to absorb a lot of light. So I chose this target because I wanted to pick something that not a lot of people know about on campus. I feel like whenever I tell people about this statue, they aren't really aware of it. I think it's pretty cool. Also, I feel like there's a lot of testudos that are laying down, and there aren't a lot of them that are standing, other than the one that walks around at basketball games and has a person in it. So let's talk about how the LiDAR sensor actually ranges. So here we're going to talk about how the LiDAR system actually works. So we have this laser, it's impinging on a target, and then some of the light from that contact is bouncing back into a camera. Now, there's a known distance, h, between the laser and the camera, and so when we hit the target with the laser, we're able to determine the range, this distance between the setup and the target based on geometry. Now, how does that geometry play out? So basically, we have this distance that we can calculate based on the geometry of the setup, where the angle between the laser point and the camera can be mapped from pixel space, which is what we're measuring, to angles, so we can actually take the tangent of it, and then we have an offset that compensates for alignment errors. So plugging that in, we have this equation, which allows us to take a picture of a laser and turn it into a distance. So here we have an example of this theoretical framework in play. You see that as I back up, the laser gets closer and closer to the center of the camera frame, and as I get closer and closer to the camera, it starts to move to the edge of the frame. So why are we interested in doing this at all? Well, much like radar, LiDAR is a remote sensing process by which you're able to send out photons, and then in many scenarios you time the amount of time that it takes for them to get back, and then based on the fact that the speed of light is a constant, you can figure out the distance. Now, remote sensing is everywhere. Anytime you take a picture of something with a camera, you're doing remote sensing. In this case, in addition to remote sensing via a Raspberry Pi camera, we are also employing computer vision, specifically OpenCV implemented on a Raspberry Pi, in order to detect anything green within this frame, and then track it with a yellow circle through the frame. This is an example of passive sensing because we're using ambient light to detect the environment. When we go to take data using a line laser, we're doing active sensing because we are providing the photons that we are measuring. So let's talk a little bit about how we actually built this setup. What it looks like, what each component does, and why that's relevant.
Here's a quick overview of the sensor. So over here we have a 3D printed mount, upon which is a Raspberry Pi and the accompanying Raspberry Pi camera. We have an Arduino, which is in turn powering a line laser, which we can see over here on the wall. Furthermore, it's all mounted to this 3D printed mount, which is in turn taped and zip tied to a tripod available at your local library. It's featuring a battery pack, which is in turn taped to the tripod, and that is powering the Raspberry Pi, which is powering the Arduino. The reason why I designed the sensor this way is it has very high modularity with minimal amount of external design time, and so these zip ties are a dime a dozen, so you can have quite a few of these, and if you don't like the orientation, you can kind of remove them and figure out what you want to do. Furthermore, it also has a spot for a phone to be held, so this will provide angular sensing, and so that way I can get the angle, like really the attitude of this whole device, and record that and map it to the LiDAR data that I'm getting. This setup is driven by Python and OpenCV to allow us to do the image processing. Furthermore, we also have the Raspberry Pi is Wi-Fi enabled, and so that's how we're getting the data from the sensor itself and being able to process them, or being able to share that information through the internet, and then map that to a 3D point cloud. This is the LiDAR setup in my room, and the target in question is my printer with some rocks in front of it. Some interesting geometries about this printer is that it's rectangular, and so we've got like this nice kind of consistent, very predictable geometry that we expect to return, and then we have some sort of like more complex geometry right over here with the two rocks. Furthermore, I'll also be mapping this paper towel, and I'm interested in seeing how this LED, this band of LEDs is actually going to affect it. So in the video itself, I'm having them as being blue, but that shows up really poorly in this video, and so for the most part, I'm just keeping this video in white. But I set it to blue because that way I could filter out all of the OOP. I could filter out all of the blue light with the color mask, and then only focus on the red, which was turning out pretty successfully. So we'll see how that goes.
Here we have the Raspberry Pi. You can see that there's a bunch of different files labeled, a bunch of different JPEG files that are labeled according to the angle of the Pi camera with respect to the horizontal. So this is at 0 degrees, right? This is 15 degrees pointing up. Any value greater than about 50 degrees is actually a negative value, but the way that the software works is it maps that back so that there are no negative values here, so I just kind of like wrapped around at the 0 point. We use an FTP in order to move all those files back to my Raspberry Pi, back to my computer, and then we have that all in this folder called Homework 6 Room. Right, so this is what the image looked like when it was only 0 angle, 2 degrees, 3, 4, 5, 6, 8, 14, 19, 24, 30. And so using Python and OpenCV, we're able to take the corresponding distance from the center. Let's pull that up. The distance of the pixels, the distance of the laser line from here to this line, the farther that this is, or the closer it is to this line, the farther it is. So for example, here we have a paper towel. It's a little bit closer to the camera, so you can see that it's farther away from this line. And here we have the wall, which is farther from the camera, which is closer to this line. And so using trigonometry, we can figure out exactly that range distance based on the calibration data that we took earlier. So running that script, we are able to map that to a 3D point cloud. Some interesting things from the data, which is going to come up in a second, is that the features don't really come up too well because the amount of absorption that the printer, which was the object in question, had on the light was very, very high. And so as such, it absorbed a lot of it and didn't reflect it back in the back, but vaguely make out printer lines.
Alright, here is my LiDAR setup. Here we have our scanning academic testudo. As we pan up, we can see that the amount of light that's coming off of the main shell is significantly less than the amount of light that's coming off of the bottom. And so this somewhat shows up in our data. It kind of brightens up right by the Maryland logo, so that's one of the key features of this testudo. Furthermore, there's a light source right behind it. I'm gonna have to mess with the color mask in order to only allow like a certain brightness and a certain color to go through, because that's definitely the brightest light in the frame when the camera is panned up. So that's a bit problematic. Furthermore, we have the Wi-Fi out here is actually quite bad, and so as such I've brought over the Ethernet cable in order to maintain a steady connection with the whole setup. And that is the method by which I am scanning academic testudo. So here we have coded academic testudo in what appears to be a toga, making him? Yeah, I'm gonna go with him. Much more easily identifiable. That red laser is highly reflective, and if we kind of pan up, you can see off of his head there's a very sharp contrast, right? This is all about like the scattering constant for the material. All right, so we're back. We have testudo covered with a nice white reflective background, so the scattering constant is extraordinarily different. This cotton material, which is a bed sheet, is able to reflect the light very well, and you can see it's a very stark contrast between the background and testudo himself.
So in total, a total of 3 scans were collected, and here's a view from another side. Okay, so today we're going to talk about how we took all of these scans that we did outside from the Friday folder, and then have them into 3 different text files. We've got the front text file, the left text file, and the right text file, correspond to those respective, respect to the academic testudo. So going into the MATLAB folder, or going into the MATLAB file, so the first thing we do is we import each of the scans as A, B, and C respectively. And then what we do is we orient the scans, so that way they show up on the plot appropriately with respect to each other, because they all kind of share the same origin originally, even though they're different parts of the same statue. And so that's what these lines are doing. So essentially, we're breaking them into their X, Y, and Z components, and then manipulating them, and then adding them back, and then concatenating them back into the same array. And so we do that for B and C scan, and then A we leave as the reference frame. And so we combine them all together into E. And then we break that up into X, Y, and Z coordinates, useful for creating the axes. And then once we run this code, this line of code will export this new E array, which is a combination of all 3 scans, kind of scaled and then transformed so that they are in the right position with respect to each other, and then exports that as a PLY format, which we can see in MeshLab. So this is actually what it ends up looking like. So there's a decent bit of noise, which we're going to clean up later in MeshLab, but essentially we have what looks like the outline of academic testudo. So you can see this is one of his arms, and this is the other arm. Something that wasn't super clear was the back, so we didn't have good access to the back of academic testudo, which you can kind of see in the video. So just a quick update to this. So here's what the testudo looks like in MATLAB. You can see that there's quite a lot of noise, which is filtered out in Cloud Compare, but all the main features, the book, the head, and the legs are still visible. The one thing that didn't really come out was the back. And so overall, I'd say this doesn't really represent what the testudo looks like in reality, and it's kind of more of like an evocation than a representation of reality. Testudo brought into Cloud Compare, we're producing some normals so a mesh can be generated. Throughout this process, we've experimented with a bunch of different kind of meshes. The first thing that we did though was to eliminate the internal points, because those should not be encountered in the mesh. And I noticed that by having them in, here they are right there, and deleted. By having them in, it created a lot of errors, or a lot of problems with the mesh generation. So I went ahead and deleted them. Here we can see that when we generate the mesh, initially using just basic settings, it's quite globular. So we went in and just kind of toyed around with all the settings until it looked like we wanted it to look. So we got kind of less globby, but we still see a lot of free-floating meshes that aren't continuous. And so what we want to do is reduce that by kind of making it a little bit more globby. Using this different mesh format, we were able to have a sheet that was generated, which we later get rid of in Mesh Mixer. But by kind of combining the best scans together and saving it as an STL, and bringing it into Mesh Mixer, cutting away some of these, some of the sheet, you see that when it exported, some of the surface normals were pointing inwards, and so by making this a solid, we can sort of get rid of that problem. And so here's sort of what it looks like. And by adding a few primitives, we can make sure that any disparate floating bodies can be connected. Using, for example, the cylinder, we're just sizing it so that it fits appropriately, and then can connect the head to the rest of the body, as we can see here. And then we're adding a sphere to just kind of keep all the internals together. The sphere is purely structural. It doesn't really show up too much in the actual mesh. It just sort of holds any free-floating bodies together. And that's sort of what it looks like. All right, we cut off the back so it's more true to form, and that's the final mesh. Huge shout out to Dr. Mitchell for teaching this class. I had a great time and I learned so much. To close out, I'm just displaying some of the selfies I took through the course of this project, as they were highly encouraged. Enjoy.